I'm gonna go over something that you should know about, or at least have some experience with. We talk about relative velocity today, okay? So you probably remember this from grade 11. What do you think it means? Kubika, what do you think relative velocity means? You don't know. Give me an example of something that's relative. What's relative? Is height relative? It's not? It can be. I mean, you can think of it as being relative. I guess I could say I'm taller than Maria, but then I would be shorter than Mr. Ruddy. But the actual length itself isn't relative. It's absolute, right? So what we're talking about here is velocity in relation to some other thing. So in relation to your desk, right now you're sitting down, right? Your desk is not moving, you're not moving. What do you think your velocity would be in relation to your desk? It would be 0. So for this one, it would be 0. What about for the Earth? Well, are you moving? If you pick a fixed point on the Earth, like the ground just below your feet, is that moving relative to you? No, it's not. So that would be also 0. But how about relative to the sun, though? Because you're on the Earth, and the Earth is moving around the sun, and well, actually, in the next chapter, we're going to calculate how fast. Okay? So I don't know what the actual number is, but it's actually pretty fast. You can figure out the diameter of the orbit, and we know it takes, how long it takes is 365 days. We can figure out the speed. It's pretty fast. Okay? It's definitely not 0. So it's velocity in relation to something else. So let's look at an example like this, okay? Number 2. You have a car that's going north. We'll call it car A. Alright? So here's car A traveling north, and it has a speed of 20 meters per second. Call this one A. Now beside car A is car B, which is traveling 30 meters per second. Now imagine you're the driver, car A. What would it look like? What's going on? You look at B. What happened? If you're traveling the same speed, it would look like you're not moving relative to that car beside you. But they're not traveling the same speed. Who's traveling faster? B. So what would B look like in relation to you? B would be moving which way? North. And you would appear like you were moving south. Because in relation to B, you are traveling 10 meters per second less. In what direction? Relative to A, it would look like you're traveling 10 meters per second south. Okay? So, in relation to the ground, you're both traveling north. But in relation to B, you would actually be traveling 10 meters per second south. Let's look at 3. Car is traveling 30 meters per second north. The driver throws a water balloon out the window with a speed of 3 meters per second south. So, car is going north. So you're in a car. The car itself is traveling 30 meters per second north. You throw out some garbage, and sorry, not garbage. That was the original question. I changed it. We don't want to promote littering. So I changed it to a water balloon. I guess that's still littering. And we throw the water balloon opposite direction. The moment the water balloon leaves your hand, what is the speed? So if you were like an observer watching this water balloon, what would it look like it was at that moment in time? As soon as you let go of that balloon, what would it look like it was traveling? Which way? So right now, imagine the water balloon is in your hand, and you're driving 30 meters per second north. What's the speed of the water balloon? Can't answer the question until I say to you, relative to what, sir? Relative to the driver, the answer would be what? 0. Because it's in your hand. You're in the car. Right? So it's relative to you, it's the same. 0. But, if you were an outside observer, watching this water balloon being held in someone's hand, it's moving. Because the car is moving. So the balloon has a speed of 30 meters per second north. If I drop that balloon, it's going to fall to the ground, but it's also going to move 30 meters per second north. If I throw it out the window, though, the speed of the water balloon will have to be the sum of those two speeds. Because it's initially going 30 meters per second north, but then I toss it 3 meters per second south. So the combined speed to an outside observer would actually be 27 meters per second north. Okay? Now I'm going to show you a question that looks very similar. Alright, look at the 4. By the way, we'll quantify 3. I have a formula that you may recall from last year. Okay? For me, 3 is like common sense, but I'll put it down as a formula so you can see it, okay? So, car's traveling 30 meters per second north and turns on its headlights. Alright? The speed of light is 300,000 meters per second. What is the speed of light? Let's put a period there. What is the speed of light as measured by a driver versus someone outside the car? So imagine you're in the car and you turn the lights on and you can measure, you can't really, but imagine you could. You can measure how fast that beam of light was bolting away from you. So let me draw a car. So here's a car. Alright, there it is, my car. Alright, here's the driver in the car. Alright. Car's going 50 meters per second this way. I turn on the lights. The lights are traveling 300,000 meters per second that way. Relative to the driver, how fast is the light moving? Now, how fast is the light moving? But also, if someone was watching outside and watching the speed of that light, what's that? You would think, right? It's not. Light is different. And there's something called special relativity. And we'll talk about that when we get to Einstein. Right now your world is normal and predictable. But later on, we're going to talk about things like relativity and quantum mechanics. And you're going to be like, you know what? You're going to come out of this course knowing less than you did coming into the course. Okay? Yeah, trust me. It sounds weird, but that's my goal. It's to actually make you know less. So the answer to this question is, it's the same because of something that we haven't studied yet called special relativity. If you want to look into special relativity, you're like, what is this guy talking about? Has he forgotten his medications? You can go ahead and look at it if you don't believe me. But we'll come back to this later, okay? So right now, our world is simple. It's more like question 3, alright? Where we add up velocities or we subtract them. So let's take a look at a formula that you may recall from grade 11, because this actually explains the water balloon. Do you remember this formula? So this is an object relative to the ground. Relative to ground. Okay. This is the medium relative to ground. And this is the medium relative to object. So if you think about the water balloon scenario, the water balloon speed relative to the ground, so the water balloon is the object relative to the ground, would have to be the sum of the medium to the ground. Now in this case, the car is the medium because the car is what the water balloon is in initially, plus the object speed relative to the medium when you throw it out the window, which is 3 meters per second south. That's why we add those two values up. So let's look at an example like this. This number 5 is exactly the same as a water balloon, but instead of a car, I give you a train. Instead of a water balloon, I give you a passenger that's moving. Okay? So a train is traveling 20 meters per second north. So we have a train going north. Okay? 20 meters per second. And we have a passenger going 3 meters per second south. But obviously, this would be the speed of the passenger on the train. So this is the passenger on train. This is the speed of the train relative to what do you think? Well, what's the train on? The ground. Train tracks, right? So, if you were an outside observer, actually, let's imagine you were a passenger. You're a passenger sitting on that train. You were sitting on the train, and you were watching that other passenger. What would that passenger look like? He was walking which way? How fast? 3 meters per second south. Right. But if you were someone outside the train watching that passenger, you would think something totally differently. Okay? So what would you think? Well, if you go back to this formula of VOG, so the object relative to the ground, well, in this case, the object is the person, the passenger, relative to the ground. Well, that would have to be the sum of what two things? It would have to be the medium relative to the ground, and that would be the speed of the train, plus the medium relative to the object, so the object relative to the medium, which is the speed of the passenger in the train or on the train. So that would be what? The train is going 20 meters per second north, plus the object on the medium is traveling 3 meters per second south. So if we make south negative, that would be 20 minus 3. So that would be 17 meters per second north. Okay? That would be 17 meters per second north. So, this is a simple question because it's only one directional, right? We're just going north or south. What about if we have two directions? Same idea. The idea is still the same. So here we have a swimmer begins to swim. Speed of the swimmer is 3 meters per second. North, 30 degrees west in the river. So imagine we have a swimmer going north. So north, 30 degrees west. So we'll make that 30 degrees. And the speed of the swimmer is 3 meters per second. Now, this would be the object in the medium. This is the swimmer in the water. Okay? Now, the river has a current of 2 meters per second. The current is always measured, well, should be always measured relative to the ground. So this is the medium speed relative to the ground. And that is going 2 meters per second northeast. So this way. Now, northeast means what angle? 45. Okay? And the magnitude of this is 2. So this is 2 meters per second. So this is VOM, object relative to medium. This is VMG, medium relative to ground. So these two have to add up to give you your object relative to the ground. If you think about it, the object is the swimmer. If you were on the shoreline watching the swimmer, it would make sense that the result of what you're seeing is the sum of the swimmer speed in the water, the object in the medium, plus the medium itself. So we could say that the object relative to the ground would be the sum of the object relative to the medium plus the medium relative to the ground. Now the object is the swimmer, so if you want to change it to swimmer, and the medium is what? The water. We can change our labels if that is better for you, okay? Now, when we add vectors, I would recommend you do the vector component method, which means you look at the vectors and you split them into x and y. So we'll take this vector over here, okay, and we look at it and we break it up into x and y. So this is my x component and this is my y component. So this is the opposite side for x, so what do we use? So we use sine. So sine 30 times 3, or hypotenuse is 3. And the y component is the adjacent side, so we use cosine 30 times 3. Okay, so what are our components for x and y for VOM, which is the swimmer relative to the water? So this is 1.5, and this is what, 2.6? Okay. Now we can do the same thing on this side. We can look at the x and y for the medium, which is the water relative to the ground. We did the exact same thing. So here's my x component. Here's my y component. So it's 45 degrees, so the answer will be the same for both. So x is sine 45 times 2. Y is cosine 45 times 2. So I believe that's about 1.4, right? 1.4, 1.4. Now, I consider sines. So step 1, break the vectors into their components. Step 2, look at the signs, okay? So for this component, it's pointing west, so if I make west negative, then I'm going to make this negative. The y is, I'll make south negative and west negative, okay? So both of these y components are pointing north, so they're both going to be positive. This component is pointing west, so it's negative, but this is pointing which way? East, so that we'll leave that as positive. Then what we do is we add up, because if you look at your formula, it's the sum of, right? We have to add up those components. So we're going to add the negative 1.5 with the 1.4. Okay, I'm going to add this one with this one, and then we're going to add this one with this one. So 2.6 plus 1.4. That's going to give us our sum. So what's this? This is negative 0.1, and this is 4. Okay? Now, this is saying that if you, remember, these are components, right? So this is saying that it's going which way? East or west? West. And the component for VSG, or the swimmer relative to the ground, looks like this. So it's pointing west, and it's pointing west with the speed of 0.1, but it's also pointing north with a speed of 4. This is obviously not to scale. So all we do now is we figure out what this is, our hypotenuse. Okay? We could just use Pythagorean theorem, do the sum of the squares. It's probably going to be very close to 4, because the sum of 4 squared plus 0.1 squared, I would imagine, is probably like 4.00 something. So I would imagine it's going to be 4. Okay? And then we could figure out the angle, right? We can use opposite over adjacent, and we can figure out what this is. So inverse tan of 4 over 0.1. So what would the inverse tan be of 4 over 0.1? That would be your angle. And it should be quite large. What is it? 89? 89 degrees. So we could write or state this two ways. We could say that the swimmer speed relative to the ground is 4 meters per second east. See, this component is east. West. West 89 degrees north. Or we could say from this point over here, we can say it's north. But then if this is 89 over here, this must be what? 1 degree west. Either way is fine. Okay? Let me show you another one that looks similar. This is the last one we'll do, then we'll stop. It looks similar, but it's not. Okay? The method is similar. So in this next question, we have a plane wants to head 100 kilometers north in 30 minutes. We have a wind blowing from the northwest with a speed of 50 kilometers per hour. What should the speed be of the velocity of the plane be to reach the desired destination in the desired time? So here's the thing. This is pretty obvious. The wind is the medium relative to the ground, and that's 50 kilometers per hour. Which way? Northwest. But it's coming from the northwest. So it's actually heading in the opposite direction, which will be southeast. So be careful. Sometimes you're told the wind is blowing from. That means the direction of the wind is actually the opposite. Sometimes you're just being told the wind is blowing in that direction. In that case, that's the direction. So if the wind is blowing south, it's south. If the wind is blowing from the north, then it's going south. Okay? Okay. The plane wants to head 100 kilometers north in 30 minutes. That's pretty easy to figure out as a speed. We know the velocity is going to be the displacement over time. So that's 100 kilometers north in 30 minutes, which is half an hour. That gives us a velocity of what? 200 kilometers per hour north. Another question is, okay, what is that velocity though? Because if you remember your formula, there is 3 things in the formula. Okay? We know what this is. We know that's the air, because the medium is the air. The plane is traveling in the air, so the medium is the air. And we know it's 50 kilometers southeast. The question is, what's that 200 kilometers per hour? Is it this one? Or is it this one? What do you think it is? And there's a key here. Wants to. Yes? Yeah, it is. This is the speed that the plane must have relative to the ground to reach that destination. So this is not the speed of the plane in the air. This is the speed of the plane relative to the ground. So we can just rearrange this equation and look for this one. So that would be the object is the plane relative to the medium, which is the wind, is going to be VOG minus VMG. Okay. We can rewrite this if you don't like O. We can say the plane is the object relative to the air or wind. Plane relative to the ground minus air relative to ground. Okay? I just changed O for P and M for air. You could use A or W, A for air or Probably W for window would have been better, but okay, that's okay. So if we look, we can, again, same idea. We take this vector and we look at its components. Okay, so it's 50 kilometers southeast. So that would be this way. It's 50. Southeast means what angle? 45. So what would the x component be? Be what? Sine 45 times 50, and that would give you, what's that, 30, 36 around? Oh, sometimes I have it going southeast. Sorry. I was just testing you guys. No one believes that. Okay. I don't blame you. So it's going, okay, so the magnitude won't change, but the direction definitely will. So it's 45 degrees. Okay. Very good. So what's the value for x? What is this value? 35? Okay. I don't need to do the next one because cosine 45 times 50 is the exact same number. So we know this is also 35. We'll leave east as positive, but we'll make south as negative. Okay? This one we do not need to break down because it's already broken down for us. It only has one component. It only has a north component, so the y component would be 0, and the x component would be plus 200. Okay? So now what we do is we do the same thing we did before. We add up our components independently, but in this case we're actually not adding them, we're actually subtracting them. So we're going to subtract VPG from VAG. Yep. Yeah, again, I was just testing to see if you guys are paying attention. Oh, that's 2 mistakes. Very good. At St. Joe's, nothing gets by our students. Okay. So this is, you're right, this is plus 200. And this is 0. Thank you. Just slow down maybe. Okay. So, let's subtract. So VPG. So VPG minus VAG. So plane relative to ground would be this one. So it's going to, for x component, it's 0 minus this x component, which is plus 35. For the y component, it's plus 200 minus this, so minus a negative. Okay, so what is that? This is negative 35, and this is 200 plus 35, so this is 235. All right, so now we have now this again, this is for what? This is for plane relative to air. So this is saying that we have a component that is pointing which way? West, 35, and north, 235. So we can go ahead and figure out what this is. So we know it's the sum of the squares. So what does that give you? 238. And we could look at the angle. Again, it's opposite over adjacent. So we know tan theta is op over adjacent. So if we do the inverse tan, we will get the angle, which is what? Sorry? 82? 82 degrees. So then we can state our answer as the velocity of the plane relative to the ground would have to be, I'm sorry, plane relative to air, not ground. This is the plane relative to the air. Okay. So this is the plane relative to air. Has to be 238 kilometers per hour west, 82 degrees north. Or we could say north, 8 degrees west. Now, intuitively speaking, the answer should make sense because we're going northwest. The wind is going southeast. We go northwest at 230 kilometers per hour, and the wind is blowing southeast. The plane speed should increase or decrease relative to the ground. It should decrease. And the plane speed relative to the ground we figured out was 200 kilometers per hour. So this answer makes total sense. Okay? Alright guys, so that's relative velocity as a review. And that's the last thing in that chapter. Okay? And we will stop.